In this video, we're going to take a look back at our very first unit on numerical reasoning. If you don't know what that is, hopefully this will be a good review of what we covered. So the very first learning target was just looking at the positive or negative square roots of perfect squares. So you could have these memorized, but if you don't, it's very simple to find. If you go over to Desmos, there is a little square root button, second down on the left. If you click it, you can just go ahead and type in the number. So the first one is the square root of 121. So we'll put the square root of 121, and it gives us our answer, which is 11. Same thing for the second one. The second one is the negative square root of 225. So we put negative square root of 225, and we get negative 15. And then the last one is the negative square root of 361. So we'll put the negative square root of 361, and we get our answer of negative 19. With the next two, it's the same thing, it just writes it out in words. So the negative root would look like this, of 289. If we plug that into Desmos, we get negative 17. And if it doesn't say negative root, we assume it's the positive root. Do the same thing, plug it in, and you're going to end up getting 12. And that's it for the first learning target. The second learning target wants us to estimate what two consecutive integers a number falls between. So if you don't remember what the word consecutive means, it just means which two numbers in a row. So like 13 and 14, 7 and 8, 2 and 3, that's what consecutive means. So we can use Desmos on this one too, just to find our answer. So if we look at the negative root of 17, we get negative 4.123 and then a bunch of other numbers. What we can do is we take that whole number part, so it gives us negative 4.12310 and then whatever. If we just take this part before the decimal, that's our first number. So it's going to be between negative 4 and what comes after 4, 5. So it's between negative 4 and negative 5. Same thing with the next one. We'll put the square root of 160. We get 12.649 and a bunch of numbers. We take the first part, 12. What comes after 12? 13. Same thing for the next one. We want the negative square root of 380. That's negative 19.49, a bunch of numbers. So we have negative 19 and negative 20. And then the last one is the square root of 12. It's 3.46 and a bunch of numbers. So our first part is 3, and it's between 3 and 4. Next, it asks us what square roots of non-perfect squares are found between 4 and 5. What that means is if we square 4 and we square 5, we get 16 and 25. So we want all the numbers between 16 and 25. So 17, 18, 19, 20, 21, 22, 23, and 24. So that's all that means. And that takes care of our second learning target. Our third learning target, and where most of us had trouble in this unit, was illustrating the real number system. If you don't remember what the real number system is, that was the diagram that we had that separates the type of numbers. In that diagram, we had two large categories. We had rational numbers and irrational numbers. If you don't remember what those are, rational numbers is anything that can be written as a fraction. So 9 over 3, 3 over 4, 7 over 8. And irrational numbers were pi and the square root of any non-perfect square. So if we look at our examples up here, all of these numbers are non-perfect squares. because when you take the square root, you don't get a whole number. So the main difference is irrational numbers are decimals that go on forever and ever. They never repeat, they never end. So they're non-repeating and non-terminating. Whereas our rational numbers are the opposite. They either do repeat or they do end. Inside of rational numbers, we had integers, which were positive and negative whole numbers. So 0, 1, 2, 3. And it goes on forever and ever in that direction. And then -1, -2, -3, and it goes on and on forever and ever in that direction. So there were no decimals. It's only those things without decimals, but it could be positive or negative, or it could be 0. Inside of your integers, you have your whole numbers. Your whole numbers only include 0 and the positive integers, and they go on forever and ever. And then inside of your whole numbers, you had your natural numbers. So that's positive numbers with no decimals. Notice I did not write 0 because that is not a natural number. We sometimes call these natural numbers counting numbers because when you learn to count, you don't typically start at 0. You just start at 1, 1, 2, 3, 4, 5, 6, and so on and so on. So from there, if we know the subsets, we can work on actually classifying numbers. Remember, this whole thing is called the real number system. So all of them are going to be real numbers. So if you look at the last learning target where you have to classify, we're going to check each subset that a number fits into. So all of these numbers are going to be real numbers. So we'll go ahead and check all of them. If we look at -48/8, we'll put that in Desmos, and that gives us -6. So if we look up above in our real number system drawing in the diagram, if we have a negative number, we can't have it be a natural number, it can't be a whole number, but it can be an integer because there is no decimal in this. And then anything that is an integer is also a rational number because that subset is inside of rational numbers. So when they're nested like that, it means that they're also included in the bigger one. If we look at the square root of the negative square root of 10, if you don't know, you can put it into Desmos and you'll see that you get a fraction. What that means is it's a non-perfect square, just like -12 is. And we have a number that is irrational. Anything that's irrational is only irrational and real. It does not fit into any of the other categories. Our next one, we have a repeating decimal. That's what this line means. And remember, irrational numbers are only non-repeating, which means that ones that do repeat are rational. Oops, that's not where that check mark goes. There we go. In our next one, you'll see that 2.13131313, that 13 is repeating. And as such, that's also a rational number. In our next example, the 0.13, 113, 1113. There's a pattern, but it's not something that repeats. So it's non-repeating. And that would be an irrational number. And lastly, we have 0/13. Anytime you're dividing 0 by a number, you still get 0. And our zeros start in our whole numbers. If something's a whole number, it's also an integer and a rational number. Our fifth learning target was describing numbers in the real number system once again. My first thing that I would do if I was solving this first problem is take this list of numbers up here and divide them out and see what I get. So the square root of 5 is 2.236 and a bunch of numbers. The square root of 49 is going to be 7. Negative 1/3 is 0.3 repeating. Then we have this decimal, it's already a decimal. 15 divided by 3 is our next one that we can do something to. And we get 5. And then negative 16 divided by 4 is going to be negative 4. So if we want a whole number that is not a counting number, remember if we look back up our real number system, the only one that is whole and not natural or counting is 0. So that's the only number that we could fit in there. If we want an integer but not a whole number, we can once again look up at our chart. We look at our integers versus our whole numbers. The difference is that our integers have all of these negatives. So as long as it doesn't have a decimal and it's negative, it fits into that category. So that would be negative 16 over 4, which divided out into negative 4. If we want an integer that is not a counting number, it's the same thing. Anything that's negative, so negative 16 over 4, but also 0, because remember, 0 is an integer because whole numbers are inside of integers, but it is not a natural number. If we want a rational number that is not an integer, remember that our integers cannot have decimals. So anything that has a decimal that repeats or ends is going to be a correct answer. So negative 1/3 is a repeating decimal, the 0.33333, and that keeps going forever and ever. And then also 2.457234568. While it's a huge decimal, there's nothing to indicate that it's going to keep going. It ends at the 8. And then lastly, we want an irrational number. Remember, our irrational numbers are any square roots of non-perfect squares. So the square root of 5. Our sixth learning target was recognizing whether the sum or a product of two rational numbers or two irrational numbers, or a combination of the two, gives you a product or a sum that is rational or irrational. So in our first one, we have 12 over 15 plus the square root of 13. That's not how you put that in the calculator. Let's try that again. Plus the square root of 13. And I want you guys to be careful because we look at this in the calculator and we say, oh, it ends with the 5. But anytime you're adding an irrational number to anything, you're going to end up with an irrational answer. So this first one is going to be irrational. If you look at our next one, the square root of 3 times the square root of 3, if you plug that into Desmos, you see that it gives us 3, which is a rational number. Anytime you multiply a square root by itself, you're going to get the number inside of the square root symbol. So whether it's the square root of 5 times the square root of 5, that'll give you 5. Or the square root of 11 times the square root of 11 gives you 11. Because of this rule, that's why you have a rational number. So while you can put it into Desmos, if you need to, try to take note of that. It's something very important and that you will use in your future math career. Our next one is the square root of 16 plus 2/3. Square root of 16 is 4 plus 2/3. And anytime you add two rational numbers, you're going to get a rational answer. But if you'd like, you can also put that into Desmos. And you'll see that you get 4.6666666666666 forever and ever, which is going to be a rational number because it repeats. And then our last one, 4 times pi, is going to be irrational. If you'd like, you can put that into Desmos. But once again, you can't really tell just looking at it because it looks like it ends, but it doesn't. Anytime that you multiply a rational number by an irrational number, you're going to get an irrational answer. The only exception is if you multiply it by 0, because any number times 0 is 0. And that's all we have for the real number system. Our last learning target is putting numbers in order. So this first question tells us to put it in descending order. Remember, that's greatest to least. And my suggestion would be to change all of these into decimals. This should actually have a parentheses here. So negative square root of 136 is negative 11.66. 4.5%. Remember, anytime you have a decimal, a percentage that you want to turn into a decimal, you take your decimal and you move it over 2 places and plug in a 0. So that's going to be 0.045. Negative 2/3 is going to be negative 0.6 repeating. Square root of 5 is 2.23. 6. 2 pi is going to be 6.28, and then 8.7 times 10 to the negative 2 is going to be 0.087. What I would suggest for these problems would be to line them up vertically, so negative 11.66, 0.045, 0.666 repeating, and that should be negative, 2.236, 6.28, and 0.087. Notice when I lined these up that my decimal is going straight down and every set of numbers is lined up. So if I want to go descending order, first of all, notice your negative numbers. Be careful of those because those are actually going to be at the end. So we're just going to look one column at a time to find our biggest numbers. And for now, we're just going to ignore these two because they're negative. So if we look, going down this first row, we want the biggest thing. So we have 0, 2, 6, and another 0. The 6 is the biggest, so that's our first number, 6.28. And that corresponded to 2 pi. Our next biggest number was the 2.236, which corresponded to the square root of 5. And now we have two numbers that start with 0. So we're going to go to the next column. We're both have a 0, so we go to the next column. We have 4 and we have 8. What's bigger? 8. So we're going to put 8.7 times 10 to the negative 2 as our next one. And then all that leaves is 0.045, which is 4.5%. And now we can look at our negatives. Looking at our negatives, remember that the smaller the number looks, the smaller the magnitude, the bigger it actually is. So the negative 2/3 is going to be bigger than our negative 11.66, which corresponds to the negative square root of 126. For our next problem, we want to use this number line to approximate the square root of negative 2, the negative square root of 2. Those are two completely different things. And we get negative 1.41. So halfway, if we count these, there's 1, 2, 3, 4, 5 between negative 1 and 2. So 1, 2, 3, 4, 5. So each of these, if we're going from -1 to -2, we can count by 0.2. So this is -1.2, -1.4, -1.6, and -1.8. So -1.41 is just barely past this -1.4. And that's how we would estimate it. If you don't know how I got these numbers down here, what you can do is because between -1 and -2 is one number, you're subtracting 1. If you do 1 divided by however many spaces there were 1, 2, 3, 4, 5. So we'll divide it by 5. That tells us that it's a difference of 0.2 every time. So all I did was add 0.2 to get from one spot to the next. Hopefully you found this video helpful. If not, feel free to reach out and I will do whatever I can to help you out.